Scalability is a hot topic for blockchains. Historically, the Bitcoin blockchain can handle 4.6 transactions per second. Ethereum, on the other hand, handles as much as 27 transactions per second. These numbers are, however, dwarfed by Visa's 1,700 transactions per second. Could a blockchain reasonably compete with the scalability of a centralized payment network? Today we read the EOS technical white paper, which promises a highly scalable blockchain. One which claims to support millions of transactions per second, and also one which can support decentralized applications. Let's see what this white paper is all about. This is the White Paper Center, brought to you by Randall Richard Raymond. Okay, so to start off, the authors explain what requirements a blockchain would need to support applications that can reach mainstream adoption. First, they argue that a blockchain needs to be able to support apps that can have millions of users. Second, the blockchain platform should be able to be used freely by any user. The blockchain should allow its applications to be easily upgradable. There should be little feedback delay when a user interacts with the app. And finally, the blockchain should be highly performant and scaled to support multiple sequential and parallel tasks. The EOS blockchain architecture hopes to satisfy all of these requirements and more. EOS uses a couple interesting schemes to reach fast consensus. First, it uses something called delegated proof of stake. Recall first what proof of work is. Proof of work in Bitcoin is a race to solve a cryptographic puzzle. The winner gets to add to the blockchain. In other words, proof of work is a method by which we determine who in the network adds to the blockchain. Proof of stake is another method for determining who adds to the blockchain. Instead of basing it on races and cryptographic puzzles, the next block producer is decided using the amount of stake they have in the cryptocurrency or the network. For example, if Bitcoin used proof of stake, a person who owned a lot of Bitcoin would have a high chance of producing the next block. Delegated proof of stake is related to proof of stake. In delegated proof of stake, a set of nodes are elected. People vote to put nodes into office, so to speak. In EOS, 21 nodes are elected at a time. Each node fills a predetermined time slot. So if I was one of the 21 chosen nodes, I might be the 20th block producer to go. The 21 block producers each create a block in their given order 6 times each. Then a new group of 21 block producers are chosen. In EOS, a block is produced every 0.5 seconds. Assuming blocks can produce the same number of transactions as Bitcoin blocks, that already puts us at around 5,500 transactions per second if all goes well. On top of this high scalability, a block needs to be signed by at least 15 of the block producers in order to be accepted. This prevents fraudulent transactions from entering the chain. Furthermore, in case of forks, the longest chain is always chosen, similar to Bitcoin. As additional protection, users are forced to reference a block hash in each transaction they send out. This reference is like a confirmation from that user on which fork of the blockchain they are staked on. Accounts in EOS are a little bit similar to Ethereum. In EOS, each account can be named, and account creation comes with a fee. This fee is expected to be paid by the application developer. Okay, so accounts can send actions to other accounts, and accounts can handle those actions via action handlers. This is EOS's version of smart contracts. The EOS software defines a permission system, which can be thought of as a more sophisticated multi-signature scheme. Accounts can define permission levels, which determine what subset of other accounts and keys can issue an action via that account. For example, a friend permission level on an action would assert that an account can only send said action from one of the account's friends. Accounts define mappings between actions and permission levels. So for example, there could be a smart contract out in the ecosystem that allows one to make a buy order on an exchange. Okay, so this buy order is considered an action. A user account could define a permission level mapping the buy order to any friends of the accounts. Permission levels are hierarchical in nature and can inherit from other permissions. For example, the family permission level could do everything the friend permission level could do plus more. EOS also defines 2 permission levels. The active permission level is the default permission level of an account. The owner permission level can do everything the account permission level can do, but it can also change who the owner of the account is. Actions can have a delay. So for example, an application developer could force the action of buying a house to take, say, 30 days. This is important for security as the action can be canceled within 30 days. Okay, and finally, accounts can elect an account recovery partner who can help restore the account in the case that the private keys of the account were stolen. Now, let's get a little bit into parallelism. A fundamental idea of EOS is this idea of parallelism. In computing, parallel execution is just doing multiple tasks at once. It's important that none of the tasks rely on each other so that none of the parallel threads of execution need to wait for another thread of execution. For example, if you had to solve 100 separate math problems, one way to do this is to solve them in order. Instead, you could set up 100 parallel threads and execute each problem, drastically reducing your overall computation time. Thus, it's important for EOS to establish an environment where tasks can be parallelized. Remember, at a high level, blockchains contain blocks, which in turn contain transactions. In EOS, blocks are produced every 0.5 seconds. So how do you allow two accounts to send and receive multiple actions in less than 0.5 seconds? This is possible thanks to some important design principles that allow batches of transactions to be sent and evaluated in parallel. Okay, starting from the ground up, we have actions, and one transaction in EOS can contain multiple actions. In EOS, transactions are contained in something called a shard. Within one shard, each transaction can be evaluated in parallel, assuming no transaction modifies the same account. What happens if two transactions do modify the same account? Well, the second transaction can be added to a new cycle. Once every transaction within a cycle is evaluated, the next cycle of transactions is evaluated. Cycles are contained within a single block. So other optimizations can be made. For example, some action handlers are read-only and don't modify an account state. As a result, these can usually be executed in parallel. Some actions contain computations that are context-free, meaning they don't rely on the blockchain state. One example of this is signature verification. All you need is transaction data and the signature to run this computation. This data doesn't need to look into the blockchain or anything like that to make the computation work. As a result, these type of computations and transactions can be done in parallel. So you might be wondering how EOS determines whether a transaction takes too many computational steps. Right? In Ethereum, the solution was creating something called gas, which was embedded into the consensus of Ethereum. EOS solution is basically all about leaving it to the 21 block producers. Blockchains using the EOS software need to pay attention to three resources: disk, CPU, and RAM. Long-term storage is held in the disk space of the 21 block producers. Computations and computational backlog are managed thanks to the CPU of the block producers. And finally, state storage is possible thanks to the RAM of the block producers. These resources are finite, obviously, so accounts are barred from using more than a certain percentage. This percentage is based on how many EOS tokens the account has staked. It's important to note that some accounts may have staked a lot of tokens but don't need any resources. So these accounts can delegate their allocated resources accordingly. Finally, on the topic of tokens, as with other blockchains, block producers are rewarded with EOS tokens for producing blocks. These tokens are newly minted tokens, and the EOS software is configured in such a way that inflation does not exceed 5% per year. So, another really important topic is governance. Governance is all about reaching consensus on subjective issues and recording the consensus as new community laws. So, governance is also important when it comes to checking power. Block producers, for example, can be very influential, and if left unchecked, can be too powerful to contain. One example of the block producer's power is the ability to freeze an account. An account can be frozen if the block producers refuse to include any transactions being sent to or sent by an account. This can be the right thing to do if an account has problematic code, but if done unethically, stakeholders in the ecosystem can vote the block producers out. Block producers also have the ability to completely swap out the code of an account. If there's some security vulnerability in an account, this might be the right thing to do. But if this power is left unchecked and block producers do this in the wrong way, people can vote them out. The authors state that there isn't any virtual machine or scripting language that is defined as a part of the EOS software. The argument is that these are implementation details. As a result, most information that's either passed as actions or stored as state are defined by a schema that can be seamlessly converted into a human-readable format such as JSON. Finally, EOS supports communication with outside blockchains. The basic premise is that there needs to be a way of proving that a transaction was included in the block of some blockchain. This is possible thanks to Merkel Trees, which are data structures that hold hashes, and hashes are digital fingerprints. Using Merkel Trees, it can be relatively quick and resourceful to determine whether a transaction exists in a blockchain. So in conclusion, the authors introduced EOS, a software specification for a blockchain that can scale to support a large number of transactions and applications. Thanks to delegated proof of stake and a commitment to using parallel execution, EOS offers a model of scalability that is definitely promising. And that's all we have for you today. In our next episode, we'll be doing a guided reading of the 2018 version of the Elastos white paper. See you next time.